Friends, welcome to another session of All 4 e-learning program. Right? This is physics session number 62. Now, in this session, we will talk about equipotential surfaces. Equipotential surfaces. Now, before going to this, let's have a recall of what we have studied in the earlier case and what are the various things that are useful for the understanding of this topic there. So, I was telling you, charge is a fundamental quantity, charge exhibits field, lines of force. Wherever there are lines of force, there is electric field spread over it, and even in the field there is work to be done in getting a charge. Then the work done in moving a charge from infinity to the point is potential. Actually, electric potential is the electric state of the body. It is the electrical state which determines the direction of flow. It is defined as, the electric potential is defined as the work done per unit charge. The work done in moving a unit positive test charge from infinity to the point of the field. Potential. Well, now the potential difference between 2 points is the work done in moving the charge from initial to final per unit positive test charge. So it is the work done in moving from initial to final per unit positive test charge. Later, potential is potential due to a point charge. We have deduced a formula for the potential due to point charge. It's 1 by 4 pi epsilon naught q by d. If d is the distance of the point and the potential due to point charge is like this. If there are many charges, the potential is the algebraic sum of all the charges. It is the algebraic sum of all the individual potentials. Potential due to individual charges, the sum of all the individual potential is total potential. Well, then we have deduced a formula for the potential due to many charges, different charge distributions, charge potential energy we have learned, all those things like this. Now let us understand the potential due to let us understand equipotential surfaces. The term itself will suggest you that it is equipotential surface. It is a plane, plane surface, where the potential at all the points is same. The surface where the potential at all the points due to the charge distribution is same. Now that surface is termed as equipotential surface. What is the significance of an equipotential surface? The equipotential surface is a surface where the potential is same. The work done in moving any charge from one point to another point in that surface is zero. There is no work done in moving any other charge from one point to another point in that surface is zero. Now, how do you let us understand. Now, consider a point charge. Let's take a point charge Q. Right? Then, due to this point charge at a distance R, now what is the potential at this point? Potential due to this charge at this point P. Point P. So potential at that point V is 1 by 4 pi epsilon naught. We have already deduced the formula for the potential due to point charge. 1 by 4 epsilon q by d. We have derived this by taking potential as work done per unit charge. I was getting a test charge from infinity, placing at this point. So we have deduced the formula. So the potential is 1 by 4 pi epsilon naught q, the charge q, by the distance of the point r. Right? It is the work done in moving a unit positive test charge. Electric potential is the parameter linked to the charge q, not the test charge that is being brought and placed at that point. It is not the fact, it is not the property of the charge that is being placed here in getting it from infinity. It is the property of the field or the charge that is this charge. It is the property of this charge. So it's 1 by 4 pi epsilon naught q by r. Now let me consider the same point here at the same distance. Then the potential is, potential is a scalar. It is just a mere number and a unit. It has no direction. So potential at this point is also same. Now let me consider all the points which are at equidistant from that point charge. The locus of all the points which are at equidistance, it's a sphere in a plane or it's a circle in a plane. If I take all the points in 3-dimensional space, I get a sphere. All these points are at same distance from this point charge. From the point charge, all the points are at same distance. Now the charge is Q and all the points are at same distance. This is Q and this is R. This is same for all the points. So for all the points the potential is same. Now at all the points on this surface the potential is same. It's a constant. Now that surface is termed as equipotential surface. Now that surface is equipotential surface. Now suppose if I take another distance from the point charge, let me take a smaller distance R1, then I get a equipotential surface like this. Another distance R2, I get a equipotential surface. R3, another surface. So for a point charge, there are infinite number of equipotential surface I can take. It is a family of concentric spheres. You see, this is a smaller sphere of radius, small value. Another sphere, another concentric with the point charge. Right? So for a point charge, there are infinite number of equipotential surface. A family of concentric spheres around this point charge will form equipotential surface. Well, each one has got its own potential. Let's suppose the first layer. This is the charge. This is the charge actually suppose. First layer potential is V1. At all these points the potential is same V1. Another layer like another spherical layer like this. The potential is V2. So at all the points the potential is V2. Third layer potential is V3 like this. So they are concentric spheres. For a point charge the equipotential surfaces are concentric. A family of concentric spheres. Infinite number. At different point potential is different. Well, in on different surface potential is different. But at any point on the same surface the potential is same. So an equipotential surface is the surface where the work done in moving any charge from one point to another point on the surface is zero. There is no work done in moving the charge from one point to another point. So the potential is, the work done is zero. So potential is same. For a point charge, the equipotential surfaces are infinite. They are all concentric spheres. You get a family of concentric spheres. Well, now let us understand. For this point charge, if I draw the lines of force, we have studied in electric field concept, the lines of force from a point charge, the lines of force start from the charge and they extend up to infinity like this. Now when I take like this, consider any equipotential surface. At any point the line of force is normal to the surface. Take any equipotential surface, this one, at this point the line of force is a normal. So you can deduce, you can infer a point that the electric lines of force are always normal to the equipotential surfaces. They are normal to the equipotential surface. If I take an equipotential surface, then here the line of force is perpendicular to the surface at that point. Right? The equipotential surface are normal, always perpendicular. Equipotential surface are always perpendicular lines of force. So the lines of force at any point on the surface is perpendicular to the surface, normal to the surface. So at any point they are normal to the surface. The lines of force are normal to the surface. Another point, you see when you take a nearest point, here the potential is V1 and here it is for the next layer potential is V2, next layer potential V3, next one potential V4. As I move away, potential is decreasing, V1 is more. Inversely proportional to distance, V1 is nearer. For the same point charge Q, V1, R is less, potential is more. So V1 is more than V2, greater than V3, greater than V4. So as you move away from the charge, potential is decreasing. So in any electric field, as the surface is moving away like this, as you move away in the direction of the field, potential decreases. So in the direction of the field, as you move away, in the direction of the field, the electric potential decreases. As you move away from one point to another point in the direction of field. You see, when I move from one point to another point in along this path, the potential is same. But when I move away from one point to another, in the direction of the line of force, as you move in the direction of the line of force, the potential reduces. Right? In the same thing, if you move in the direction opposite, then the potential increases. As you move nearer, opposite to the line of force, then the potential increases. Similarly, if I consider for a negative charge, you see for a positive charge, as you move away, potential reduces. But as you move towards, potential increases. Suppose similarly, if I consider a negative charge, minus charge, you know the lines of force are, they start from infinity, they come to the point. Now, how are the equipotential surfaces? Equipotential surface is always perpendicular to the line of force. Perpendicular to the line of force. Perpendicular to the line of force. They are normal to the line of force like this. So, if I complete them, I get a sphere like this. So, even for this, they are concentric spheres like this. Different spheres have different potentials, but as you move, the potential differs. But any point on that sphere, spherical surface, the potential is same. Now, for a negative charge, V1 value is more, of course, value is more, but minus. So, it's minus V1, minus V2, minus V3, minus V4. Value of V1 is more, but negative is more, so the potential is less. Right? So, here the potential is less. Value of V4 is less, but negative lesser value is more. So, for a negative charge, as you move away, potential increases. As you move towards, potential decreases. So, from these two, what do you infer? We infer, as you move in the direction of the line of force, in the direction of the electric field. So, in the direction of the electric field, potential decreases. In the direction opposite to the electric field, potential increases. Well, direction of the electric field is given by the lines of force. Any tangent drawn to the line of force at any point gives the direction. So, if you are moving along the direction of the field, if you move away in the direction of the field, then the potential decreases. If you move in opposite direction to the field, then the potential increases. Right? So, equipotential surface is the surface at which all the points are said to be at same potential, or it is the surface where any charge moved from one point to another point on the surface, the work done is zero. Work done in moving a charge from one point to another point on the surface, the work done is zero. Now, that surface is termed as an equipotential surface. You know, for a point charge, the equipotential surface are family of concentric spheres. Different sphere has different potential, but all the points on the sphere, they are at same potential. For a negative charge, the equipotential surface are like this. Now, what do you infer from this? Now, when I draw lines of force, you see at any point the lines of force are perpendicular to the equipotential surface. So, the electric lines of force are always normal to the equipotential surface at any point on it. Suppose if the surface is like this, then here the equipotential surface will be normal to it. This is normal to it. This is normal like this. So, at any point the equipotential surface will be normal to the surface at any point. Now, what do you understand normal? At any point on the equipotential surface, the electric line of electric field is always perpendicular to the surface. The component of the electric field parallel to the surface is always zero. Right? So, this implies that on any equipotential surface, consider any equipotential surface. Let the equipotential surface be at this point. So, at any point, the electric line of force is perpendicular to the surface. So, the electric field is perpendicular. Electric field will have a perpendicular component at that point on the surface. The component of the electric field parallel to the surface is always zero. Parallel to the surface is zero. Electric field exists only perpendicular to the surface. The component of the electric field parallel to the surface is always zero. It has to be zero. There exists no electric field parallel to the surface. There exists only a perpendicular component at that point. Right? So, the resultant electric field will be in this direction. So, this component is zero. The component is 0. You can prove it actually. You can prove this. Now let's consider a metal conductor. Let's suppose this is a metal conductor like this. Now let us prove that the electric field is normal. The lines of force are normal to the metal conductor. Suppose if I consider a metal conductor here, at any point on the surface of the conductor, the potential is same. For a metal conductor, the surface of the metal conductor, the potential at all the points on the surface, the potential is constant. It is a equipotential surface irrespective of its shape and size. Now, at any point, suppose if I consider how like this, how? Let me prove it. Let's suppose this is a charge conductor and there the electric field is in some direction, we don't know E. Let it be in this direction. So the resultant electric field is like this. So at this point, let the angle made with the surface be theta. So the parallel component is E naught. Let it be E naught. So it's E naught cos theta and the perpendicular component is E naught sin theta. Now let me consider another charge q which is moved in a closed path inside like this. I am moving another charge q. I am moving a charge q along a closed path shown by these arrows. Right? This path A, B is inside the conductor, C, D outside the conductor. Now suppose if I am moving a charge from A to B, we know inside the conductor the electric field is 0. So the force inside the conductor on the charge is 0. So the work done in moving from A to B is 0. So work from A to B is 0. Well, B and C here. Now there is electric field, so there is some work done. Now if there is any field existing while moving from C to D, there will be some net work done which is not 0. Well, B to C, C to D to A, both are opposite, they may cancel. But A to B there is no work, but C to D there is work done. Well, B, C and C, D they are opposite, they may get cancelled. But the total work done in moving this closed path is not 0, because A to B it is 0, B, C and C, D cancel, but D to C, if there is a parallel component of electric field existing on the surface, then there should be some work done in moving from C to D. So the net work done in moving in a closed path is non-zero, which is impossible, because electric field is a conservative field. Electric field is conservative field. What is a conservative field? The work done in moving in a closed path in that field is net work done is 0. In a conservative field, the net work done in moving in a closed path is always 0. We know electric field is a conservative field. So in any electric field, the work done in a closed path must be 0. But if I consider a parallel component, then the work done in this closed path will not be 0. So electric field being conservative field, the work done in a closed path must be 0. So work done in closed path 0 in the sense, there must not exist any parallel component. So this parallel component should be 0. So E naught cos theta is 0, or cos theta is 0, theta is 90. So the electric field is not in this direction, it should be in this direction. So the electric lines of force are normal to the surface. Now just now I have said the equipotential surface always, lines of force are always normal to the equipotential surface. So the electric line of force is field is normal. So here the potential must be, the equipotential surface must be parallel to it. So therefore equipotential surface is perpendicular to the field there. Now we know electric field is a conservative field. In a conservative field, the work done in a closed path is always 0. Work done in a closed path should be 0. So work done in this closed path must be 0. Well, this is from A to B it is 0 because there is no field. B, C and C, D will get cancelled because they are in opposite direction. So D to C, then if the total work is to be 0, then the work done from C to D must be 0. Work done will be 0 if there is no force. There will be no force when there is no field. So there is no field parallel to the surface. So parallel to the surface, field is 0. So theta is 90. So the resultant field should be perpendicular to the surface. So the field is perpendicular to the surface. We know equipotential surface are perpendicular to the field. So the surface of the conductor is a equipotential surface. At any point you consider on the metal conductor, the lines of force will be normal, and equipotential surface is always normal to the perpendicular to the lines of force. So for any metal conductor, when I consider a metal conductor, then at any on the surface of the conductor, at all the points the potential is always same. This is a equipotential surface because the electric lines of force always normal to the metal, they are always emerge perpendicular to the surface of a metal conductor, right? So the locus of all the points in the electric field where the potential is same is termed as equipotential surface. The locus of all the points in a electric field where the potential is same, that when I combine all the points together, that is a equipotential surface. So equipotential surface can be a surface of a body. It can be the surface of a body, or it can be an imaginary surface, a curved surface in the field. But at any point on the equipotential surface, the potential is constant, and at any point the electric lines of force are normal to the lines of force. The lines of force are always perpendicular to the equipotential surface. So suppose if I consider a metal sphere, then for a metal sphere, well, at all metal sphere, there is no charge inside. All the charge lies on the surface of the sphere, and all the points on the surface, inside the surface, the potential is same. At all the points inside, the potential is a constant. If I draw a graph from center to surface, and then if I draw a graph for the potential like this, from center to surface, it is a positive charge. At any point, the potential is same. So from here to here, the potential is a constant. From here to here, the potential is a constant. The potential is a constant like this. Well, outside, the potential reduces. Outside this side, the potential reduces like this. Positive charge, potential decreases as rectangular parabola, inverse square law. Right? At all the points inside, the potential is same. The surface of the metal conductor, all the points on the surface also, the potential is a constant at any point. Right? On the metal conductor, now if I take a concentric sphere around it at some distance, then at all the points the potential is same. Even for this I get concentric sphere, the family of concentric spheres, the potential is a constant. Equipotential surfaces for a metal conductor is defined like this, given in this form. Suppose if I take a uniform electric field, where the electric lines of force are parallel like this. If I consider a uniform electric field where the electric lines of force are parallel, then the equipotential surfaces are planes. You see, consider all the points perpendicular here. Now these points. So this is a plane where all the points are same potential. So this plane, an equipotential surface. And another plane here, another equipotential surface. Here the potential is V1, potential V2. Another plane V3, another plane V4. So as I move away in the direction of the field, so I was telling you, when you move away in the direction of the field, potential decreases. So V1 greater than V2 greater than V3 greater than V4 greater than so on and so forth. So as you move away, potential. So this is a plane A where the potential is VA at all the points. Plane B where the potential is VB at all the points. This is plane C, potential is VC at all the points the potential is same. So as you move away, potential in the direction of the field, as you move away in the direction of the field, potential decreases. Right? So in the direction of the field, potential decreases. So in this direction, potential decreases. But if I move in the direction opposite to the field, the potential increases. the potential is increased, because in moving a positive test charge against the field, the external agent has to do work. When it does work, it spends energy. So when energy is spent, the charge system will gain potential. Energy of the system will increase. So as you move against the field, the potential increases. As you move in the direction of the field, potential decreases. So for uniform electric field, the equipotential surfaces are parallel planes like this. The planes parallel to the electric field, right? These are the electric potentials. Similarly, if I consider a dipole, if I take a dipole like this, equal and opposite charges, minus q plus q. You know, for an electric dipole, we have found the potential on the equatorial line is 0. So the plane perpendicular to the axial line, at all these points the potential is 0. It is a equipotential surface with 0 potential. Null potential surface it is. It is a null potential surface. Is it? For a dipole, the potential at this point is right side of it, the potential will be positive. You will be getting spheres like this, right? Left side of it, the potential is negative. You will be getting sphere like this. So equipotential surface are spheres this way. Right side positive, left side negative. But on the equatorial plane of a dipole, the potential is 0. 0 potential point. 0 potential plane like this. For electric dipole, the equipotential surfaces are like this. So equipotential surfaces are planes. It is a plane, right? It can be parallel planes like this or concentric spheres. You know, for non-uniform electric field, suppose if I consider a non-uniform electric field, right, diverging field like suppose, then the equipotential surface is a curve, because at any point if I draw, the surface will be perpendicular to the line of force. Here also perpendicular to the line of force, perpendicular to the line of force, then it is a curved surface. So the equipotential surface is a imaginary surface, curved surface, or a plane, or it can be a surface of a solid body, metal conductor. Then at all the points the potential is constant. The work done in moving any charge from one point to another point on the equipotential surface is always 0. No work is done in moving a charge from one point to another point on the same surface 0. But there is work done in moving from one electric equipotential surface to another equipotential surface. Well, if you have to move from here to here, there is work done. From one surface to another, there is work done. But work done in moving from one point to another point on the same surface, the work done is 0. Right? So this way we explain the equipotential surface. Right? The equipotential surface are always normal to the electric lines of force. Always at any point, the electric lines of force are normal to the electric equipotential surface like this. As two electric lines of force do not intersect, same way two equipotential surfaces also do not intersect. Suppose if two equipotential surfaces intersect like this, then according to this equipotential surface, the electric line of force should be normal to it like this. According to this surface, it should be normal to it like this. The electric field cannot have two different directions at the same point, which is impossible. So similarly, two electric equipotential surfaces do not intersect at one another. They are always separate. Two different surfaces never intersect with one another. Okay, so this way we can make out. Now again, if the equipotential surfaces are nearer, closer, right, or equipotentials are far away, by this you can even judge the strength of the field. If the equipotential surfaces are nearer, then the field is said to be strong. If the equipotential surfaces are far away, then the field is less. Suppose if I consider points A, B, C, D, E, right, field at these 3 points like this. Now here the potential between these two, let the potential between these two surfaces is some delta V, and even between these two also same delta V. Same potential difference is existing, but the separation is from the separation of the equipotential surface, you can judge the strength of the field. You know, for small separation there is same potential difference, but here the separation has increased, still further increased, it is increasing. As the separation increases, the field gets weaker. Here the field is strong. So EA greater than EB greater than CDE. As you move on, the field is decreasing. Right? Thank you.